So I think that the meeting is recording. Yeah. We will still wait for 1 minute, maybe, to let people in. I see that we have already 15 people, so that's nice. Hello, Tao. Thank you for joining.
Hi.
So, hello, everyone. We are going to start this side event that we organized with some researchers from around the world. And I will present today some case studies, but firstly I will start with a short presentation on the IAEA and also the coordinated research project. So the title of this side event is called From Yukon, Canada to the Chilean Andes, How International Cooperation can help understanding hydrological processes in glaciarized catchment using isotope-based methodology. This project is under the umbrella of the International Atomic Energy Agency. I will present you shortly the IAEA and our work here. The IAEA was established in 1957 by the United Nations as the World Atom for Peace Organization. The IAEA is an affiliated agency within the United Nations as the FAO, the WHO, the UNESCO, etc. Since November 24, the IAEA has been comprised of 180 member states. Lately, we have seen many states from the Pacific Islands joining the agency, and we are approximately 2,500 multidisciplinary professionals and support staff that represent more than 100 countries. The IAEA has 3 pillars. Of course, the most known is safeguard and verification, safety and security, but also, which is less known, is science and technology. Okay, so thank you for joining. I see there are more participants joining, and I am now presenting the IAEA and the IAEA mandates. In our case, we fall under the mandate and the pillar of science and technology. Science and technology at the IAEA include food and agriculture to promote food security and sustainable agriculture development, human health to improve disease diagnosis and treatment and nutrition, science and industry, knowledge and expertise for science and industry, environment to understand and protect the environment, and in our case, under this International Year of Glacier Preservation, our project goes through the science and technology at the IAEA under the umbrella of water resources to promote cleaner water accessible to more people and member states. We work at the Isotope Hydrology Section, which goes under the IAEA in one of the 6 departments, our Department for Nuclear Sciences and Application, and the Isotope Hydrology Section is comprised of members of staff as technical officer that provide scientific guidance to member states, and laboratory staff that develop a new methodology of application of isotope hydrology. Our objective is to provide member states with science-based information and technical skill on isotope hydrology that will help them to better assess and manage their water resources. The isotope hydrology has different roles. One role is coordinated project. This is what I will be presenting to you today, to develop new field of research and laboratory method. We also work in a global monitoring network As for example, some of you have heard of the GNIP and the GNIR network. We provide capacity building and training. For example, we work with member states to provide new technology and train our counterpart on this new technology. We also provide guidelines for the... Please kindly mute your microphone when you join. It would be very helpful. The laboratory, the Isotope Hydrology Section, also provide laboratory through a variety of mechanisms, including CRPs, TC project, and training courses. Under this umbrella of the International Atomic Energy Agency, we have developed this new coordinated project aiming to understanding hydrological processes in glacierized catchment under changing climate, using isotope-based methodologies. The background of this project is firstly based on a previous CRP that was focused on the use of environmental isotope in assessing water resources of snow, glacier, and permafrost. We also have been in consultation with member states, for example, Tajikistan, that hosted the COP29 this year. And we realized that there is a lot more to learn about glacier and glacierized catchment. The lesson that we learned from this technical meeting that was hosted in February 2024 was that glacier retreat is a serious threat to water availability in socioeconomic activities. Changes in the cryosphere increase the probability of mud flow, landslide, etc. And we have also a very largely lack of knowledge on the contribution and storage of glacier melt. Where does this water, when the glacier melt, goes? This is the main question under this CMP. The relevance of this project, as we know, it's an international concern. The glaciers are retreating at a rate that has not been observed before. And through the different COP meetings that have been occurring in the last years, on the COP27, the COP28, and the COP29, we have seen that glacier retreat is one of the main topics that is mentioned during this important international meeting. So it's really of concern right now, and we really need to understand more the processes that include this glacier retreat and where, as I said, does this water go. The objective is to support member states to develop and apply isotope-based methodology to improve water resources management in glacierized catchment under changing climate. We aim to characterize hydrological processes in glacierized catchment related to changing contribution from snow, glacier ice, and subsurface ice in water resources. This project includes countries. For example, we have participants from China, Uzbekistan, Chile, Peru, Bolivia, and Canada, and Slovenia, and England. So it's a worldwide project with many different scientists that are working on the topic of glacierized catchment. The proposed activities are mentioned this way. Our idea under this CRP is to define hydrological end member and establish a protocol for sampling program and application, establish monitoring network in the glacierized catchment, precipitation, stream flow, groundwater, water processed by the cryosphere end members, and additional tracers. We also aim to initiate the development of novel tools, for example, atmospheric water vapor, AI model, and integration of AI into water processes forecasting. Another proposed activity are the quantification of isotopic value of the selected end members and select additional tracer, apply radioactive environmental tracer to date ice layer and quantify the contribution of ice melt to runoff from glacier surface, share and exchange the knowledge between the participants of the CRP, expand the knowledge of ice dating using multiple tracers, for example, tritium, and we will also include other tracers as, for example, argon-39. We will contribute to the global and the GNIP and the GNIR network. The overall expected outcome of this project is to have more experienced participating member states in the implementation of environmental isotope for quantification, temporary and spatial variation of contribution of cryosphere components to surface and groundwater in glaciarized catchment using isotope-based methodology. We aim to broaden the scope and applicability of isotope-enabled hydrological models to gain deeper insight in the interaction of hydrological components in the glaciarized catchment and strengthening the accuracy of analytical capability of mixing models. Finally, the last expected outcome is a better understanding of the complex water mixing processes in glaciarized catchment for optimal water resources. I thank you very much for listening to this presentation of the IAEA and what does the CRP projects include. I will now give space to my speaker of today. I'm really honored to host 3 speakers that will present you work that have been done in Yukon, Canada, and in the Chilean Andes. The presentation will now started. I will stop sharing my screen and let space for my speaker. If you have any question, please welcome to ask the question at the end of the presentation. Thank you very much. So I will stop sharing. Sorry about this. I cannot find. Sorry. I don't know why I cannot stop sharing. Thank you. Thank you for your patience. I leave now the floor to Sarah Sapper, who is going to present her work in Yukon, Canada on methane emission from subglacial meltwater. Thank you, Sarah.
Thank you very much, Melanie. Could you just confirm that you're seeing my slide?
We do see your slide. Thank you.
Okay, perfect. Thank you very much. Well, good morning, good afternoon, or good evening to everyone, depending on where you're joining us from. My presentation is going to be about methane, more specifically methane that is dissolved in subglacial meltwater from where it then degasses to the atmosphere. Methane, as we all know, this very potent greenhouse gas, up to 80 times more potent over a short time scale than CO2. And that this process is happening underneath glaciers has only been found a couple of years ago. So it's a very exciting and new field of research, but also a field of research with many knowledge gaps remaining. So in my short presentation, I will introduce you to one of the projects I've been doing during my PhD, where we use stable carbon and hydrogen isotopes to track down the origin of this methane that we are measuring in glacial meltwater. To understand where the methane could possibly be coming from, let's have a quick look at a sketch of a glacier. I'm not an artist, as you might can tell. So in summer during the melt season, meltwater is produced on the glacier surface through the melt of snow and ice. And this meltwater can flow along the surface of the glacier until it reaches small cracks, which it soon widens to larger channels and penetrates into the ice and flows out of the glaciers through the meltwater portal. But further up on a glacier, this surface meltwater can penetrate all the way through the ice until it reaches the glacier bed where it flows along. If the glacier is thick enough, the overlying ice exhibits such a high pressure on the bottommost ice layers that this ice can actually also melt, and subglacial meltwater is being produced, which very slowly trickles along the bed of the glacier until it joins the faster flowing meltwater coming from the surface. And we have looked at methane concentrations on the glacier surface in the meltwater and at the glacier portal. And what we've found is that in the surface meltwater and also in melted ice, we have concentrations which are at or below the atmospheric concentrations, whereas then the water coming out from the meltwater portal can be up to 100 times elevated in methane concentrations. So if we want to find out where it's coming from and what the processes are, we really have to take a closer look at the glacier bed, at the subglacial environment. If you imagine yourself standing at the glacier bed, what would you see and how would you feel there, you think? First of all, you would probably be quite cold because it's cold down there, but due to the overlying pressure, as I've mentioned, it doesn't have to be frozen. So there can be liquid water present. You might be quite out of breath because there are many areas where all the oxygen has been used up. It is dark, but if we would turn on some light, we would see that the subglacial environment is composed of large rocks, boulders, debris, different sizes, a lot of fine sediment. And then if we were to analyze the sediment in the laboratory, we would maybe find that there is also quite a lot of organic material contained in the sediment. Organic material, old organic material from times when the glaciers were smaller, had receded, and there were plants growing in the area, which is now covered by ice. And who knows what else was roaming this area in ancient times. And then further in the analysis, we would also find out that there is life in the subglacial environment, life in the form of microorganisms such as methanogens, which have specialized to be living and thriving in these very unhostile environments without oxygen. And these methanogens, they use the organic material to produce energy, and the byproduct of this process is methane. Most or a lot of this methane doesn't stay at the glacier bed, but it actually gets dissolved into the meltwater flowing along the glacier, transported to the margin of the glacier, from where it then very quickly degasses to the atmosphere. Very quickly because the concentrations can be so high. Where is all of this happening? When I first planned this study back in 2021, we were only aware of 5 sites where subglacial methane emissions are occurring, 4 of them happening from the Greenland ice sheet and 1 from a glacier in Iceland. So there was very little empirical data present about the spatial occurrence. And the motivation behind this project really was to find out where else is it happening. Is it mainly happening under the large ice sheets, or can we also find it happening underneath smaller mountain glaciers? And if we can find it, in this case specifically in the Yukon, then what is the source of the methane there? So the study area, you can see the small rectangle here in the very northwest of Canada, Yukon, the St. Elias ice field, which is the largest mass of ice outside the polar region. And we picked kind of randomly 3 glaciers to study from north to south. They're called Donjak Glacier, Kluane Glacier, and Dusty Glacier. And I've highlighted them here in green, blue, and orange. The way we did the field work was we accessed all of the glaciers via helicopter. And from the air, we were trying to find upwellings, which are those very turbulent whirlpool-like features in front of a glacier tongue where subglacial meltwater is pressed out from underneath. So these are sites where it's most likely to be finding methane should there be any produced because it's so pressurized and hasn't degassed previously. And once we were on land, we measured the concentrations of methane in the air and in the water with a portable greenhouse gas analyzer. We also sampled gas for stable carbon and hydrogen analysis, isotopic analysis, and water for the hydrochemistry. Some of the results, as soon as we started up the portable greenhouse gas analyzer, in the case of Donja Glacier, here shown in green, we had very elevated methane concentrations already in the air. And then when we collected some water and shook it vigorously and then analyzed the headspace of that with the portable greenhouse gas analyzer, we saw that there's even more methane contained in the meltwater at all three glaciers. So all three glaciers that we surveyed in this area are direct sources of methane to the atmosphere, and interestingly, there are sinks of CO2. This was all confirmed by discrete samples we collected and later analyzed in the laboratory. And concentrations we found at those sites were 45, 135, and up to 250 times higher than atmospheric methane concentrations. So that's quite high concentrations in meltwater. We then looked at the isotopes of the methane, specifically at carbon-13 and deuterium. And in this dual isotope plot, we plotted it together from samples we knew the values of other studies from Greenland and from Iceland to find out what the source of this methane is. So the samples from the Yukon here in blue, green, and orange, they plot quite differently than the purple and pink ones from the Greenland ice sheets, but somewhat still in the range of microbial methanogenesis, whereas the orange ones from the glacier located furthest south in our study, it plots clearly within the thermogenic area. However, this transition from the microbial methanogenesis into the thermogenic region can also occur due to oxidation. So just with this dual isotope plot, we could not distinguish exactly what the sources might be, if there is a mixture between different types of methane, different origins, or if there is only just oxidation going on. So we also analyzed the Bernard ratios with C2 and C3 hydrocarbon gases, whereas a threshold of this Bernard ratio above 1000 clearly indicates a microbial origin, and below that a non-microbial or a mixing origin. And all our samples from all three glaciers group very nicely in the mixing area. So we interpret our results as of being of microbial as well as of thermogenic origin, and that there is also some oxidation of this methane going on. A lot has happened in the 4 or 5 years since the planning of this study. We were able to draw many more points on the map of where this phenomenon is happening. There's glaciers in Alaska, in China, in half of the glaciers we've surveyed in the Alps, and all along the Greenland ice sheet. But it will take a much larger effort and also a lot of international collaboration to really find out more about the spatial distribution of these direct sources of methane to the atmosphere coming from underneath glaciers, and also to find out how important this source is in terms of the global carbon budget and climate change. Thank you very much. I take a quick question if you have one.
Thank you so much, Sarah, for this important presentation. We will also have a space at the end of the talk today for other questions. We will then leave the floor to our next speaker, Mas Dufresne Jani. She is working in Canada and she has a long experience using isotopes for studying hydrological processes. Thank you, Jenny, for being here today, and we are looking forward for your presentation.
Yeah. Do you see my screen?
Yes, we do.
Yeah.
Thank you.
Thank you. All right. So I'm trying to organize the screens here. I don't see you. I see the presentation. Right. Okay. Thank you, Sarah, for this nice presentation. So I'm gonna talk again about Yukon, and it's actually quite in the same area. So yes, as Melanie mentioned, I'm Janimaz Dufresne, working as a professor in hydrology in École de Technologie Supérieure in Montreal, and with here, I'm trying to use the pointer. Just give me a minute. There, that will be better. Yes. Okay. So my name is Janine Mazfren, and I work with a team here in École de Technologie Supérieure. I will present my collaborators on the next slide. And so the title of the presentation today is Isotope-Based Investigation for Deciphering the Parafluvial Flow to Proglacial Streams in Yukon, Canada. So as I mentioned, I work with many colleagues, professors and students. Michel Barrère here, also professor in glacial hydrology at the DS, and also Adrien Dimec, who is a specialist in geophysics. And in this project and throughout the years, we've been collaborating with many students, and the results and work and ideas I'll be sharing today are also coming from the work of Bastien Charana, who is currently doing his PhD, Eyal Valence as well, and Adam Trogler. So the team, we've been going on the field together, and the results I'll be talking about is actually just recently submitted paper to HESS paper, and so you will be able to find it on the web really shortly under the Geosphere number 117. So coming up in the next days. So where is it, the study location? It's again in Yukon, Northwest Canada, and we are also located in the St. Elias Mountains, but really on the side of it. So on the northeast side of the range of the mountains, and it's actually a place where we are on the leeward side of the mountains, where the precipitation are not that big. So the glaciarized catchment we are interested in are somehow deglaciating valleys that contrast with the rest of the ice field over there. So the region we study is hosting very diverse cryospheric features. So we see glacier, we see, well, actually we don't see it because it's buried, but we know that there is some buried ice, some rock glaciers containing buried ice, some debris-covered glaciers, permafrost, icing of ice. So there's really a lot to study, really different ways we can see ice, and this ice is melting at different rates because it's different features, and we're trying to understand with the use of stable isotopes how these different features are contributing to stream flows. So if I zoom in a bit in the region, we've been working for a few years in this really tiny area there, which is just few square kilometers. It's actually a sub catchment of the Grizzly Creek catchment here that is also known as Charshataga. Grizzly Creek has this name because of the Grizzly Creek Glacier there. So we've been studying this area, which has the glacier and a continuum of debris-covered glacier and rock glacier at the bottom of the valley here. And looking at historical data, we've been interested, sorry, in some icing or off ice formation just downstream the rock glacier. So this is a capture of some satellite imagery, and throughout the years, we've been seeing that some off ice are forming just at the tongue of the glacier, before the rock glacier, and just downstream. And we've been interesting to understand how are these off ice forming, and why are they not always forming. So the first off ice has been forming since the mid of the century, and is still forming quite almost every winter. But the other two are tending to disappear, let's say, or forming and not forming anymore. And this is what had shaped the work that we've been doing on the field. And we've been asking these quite general questions, but relevant ones. So what are the controls on the formation of these icing on the Chartaga or the Grizzly Creek, and what is the source of the origin that is forming these icing, and what are the implications for the downstream environment? Like, are these icing having a control on the quantity and the quality of the water that is flowing downstream there? So today I'll be focusing on data that aims to answer the second question there, with the use of stable isotopes. So I've been talking about icing, but what is it actually? It has two different names here, icing or off ice. It's actually a formation of ice during wintertime. So during wintertime, there is no or very few glacier melt or water coming from glacierized catchments, but some groundwater can flow in the area. And if different conditions meet at specific time, we can see the resurgent or appearance of groundwater flowing out of outwash or floodplains or regions like this. So we see here two different pictures. So January 4th and January 8th in 2020. So we've installed a time-lapse camera to record the formation of these icing. And what we see is that within 4 days only, there is this huge amount of ice forming on the bed of the valley there. So it really forms a big water storage, and it's interesting to understand where this water is coming from, and is it forming every year or not, and why. So we've been using a suite of different methods there. So we combine hydrogeochemistry with isotopes, a few of them, with geophysics and remote sensing methods. So going a bit more in detail there, we've been flying drones over this valley and installing some cameras to record the temperature, or using actually some thermal infrared imagery. And doing so, we've been identifying few springs here along the front of the rock glacier with very low discharge. So just an example here, this is the visible light image with the Grizzly Creek here and the front of the rock glacier. The stream is going in this direction. And if we change the image to the thermal one, we can see some contrast there in the temperature. So very low temperature of the water from this side going to the stream, and also from this side and just here. So we've been using this method to identify where is the water coming from the sides of the stream. So potentially parafilter flow or resurgence of groundwater. Why is it cold? It's because it's in contact with permafrost or buried ice. So we've been identifying, as I said before, some springs, 15 of them, and we've been trying to sample it. So all the dots here you see along the front of the rock glacier are these different springs or resurgence that we've sampled for chemistry and isotopes. So we've sampled it a few times throughout the years from 2021 to 2024, and we've been comparing the isotopic signature and the chemistry of these springs with the water that we can find along Grizzly Creek and other water we can find from the tongue of the glacier in the subcatchment, and some ice debris streams that we can see along the way. And our idea was to answer this question: are these springs fed by the water melting in the subcatchment, or are these resurgence of water coming from the bigger Grizzly Creek Glacier and flowing as parafluvial flow there and making its way back to the stream? So two streams appeared really interesting. It's actually the one that we named 8 and 9A. So these two springs are located on each side of the stream there, and it's in the really narrow section. And with isotope signature, we've been able to understand that these springs are actually groundwater contribution to the spring. And we've been trying to confirm this idea there with the use of radon 222. So we've been using it only one time, but comparing the activity in radon at these two streams with the activity before or upstream in Grizzly Creek and downstream, we were able to confirm the groundwater contribution there. So a small take-home message, what we can learn from this kind of approach. So we've been understanding that rock glaciers, as the one that we see, can have a control on the flow, on the parafluvial flow, and constraining groundwater flow paths. And so at the steady state, it resulted really in shallow groundwater resurgence with some modification of the physical chemical parameters upstream and downstream, and also it contributes to the formation of the icing. And of course, we are interested in international collaboration to see if this valley or our example of rock glacier and stream interaction is really unique, or is it something that we should assess or investigate as a more distributed processes elsewhere in different catchments area. So the future evolution is quite hard to predict, but if we can think of rock glacier degradation or ice melting, we may think that this might open more shallow groundwater flow paths, and that the flow or the quantity of water into the stream will change over time, maybe becoming less important. So this is the end of my presentation. I'd like to thank you very much for your attention, and also to acknowledge that this research has taken place on the traditional lands of the Kluane First Nation. Thank you.
Thank you very much, Jenny, for this excellent presentation. For those who have joined a bit after, we are presenting 3 case studies where isotope hydrology is used to study hydrological processes in glaciarized catchment. We had a great talk from Sarah Sapper that is actually working at the International Atomic Energy Agency. Then we have just finished the talk from Janima Dufresne that is based in Canada. We are now going to travel south toward the Chilean Andes with our presenter Francisco Fernando. We are very lucky to have him today because he is just back from Antarctica, and we are very happy that you made it back home and safe because, as we have been told, the weather was not the best. So we are very happy to see you here. There will be space at the end of the presentations for questions. And of course, we are presenting 3 case studies on how isotope hydrology can be used. But also at the end of the presentation, we will re-explain why is it also so important to have international cooperation and how the IAEA can help support this kind of international collaboration. So I'm giving the floor now to Francisco. Thank you for sharing your presentation with us. I'm looking forward to see your work.
Okay, thanks, Melanie, and thanks for having me here to share with you some of our work in South America. Well, the work is actually being currently worked in both sides of the Andes. In the Chilean side, that is what I'm working now, and also working together with colleagues from Argentina, Sebastian, that is actually also giving the presentation now. And so what I want to show you is why glaciers are so important for us in South America, and not only in Chile and Argentina, but also from the rest of the southern part of South America. So just to give you a small context, sorry, now, yeah. Well, the South America, or the southern part of South America, is actually covered by a big station of glaciers. As you can see in this figure, there is a lot of glacier extent, especially in the southern part of South America, and located mostly in the northern and southern Patagonian ice field that are shared between Chile and Argentina. But there is also quite important to see that there is a large extent of glaciers in the central part of Chile, and also close to the border with Argentina. Some glaciers are shared between both sides of the mountains. And this part is especially important because just here, big cities are located, like the capital city in Chile, Santiago, but also other cities related to the central part of Chile, like Valparaiso, where I'm based now, and I'm presenting now from. So this part is densely populated, and of course these cities are depending on the water resources that are coming from the mountains, especially from snow melt and rain precipitation that is growing in winter, is stored in the mountains, and later, as the snow melt, will be released to the low part of the country. But we are also located just in the border between the semi-arid region and the arid region, most to the north part of Chile, and the more humid part of the country to the south, where exactly in this part the future climate scenarios are showing that the precipitation is going to decrease, like in the right panel here. You see that the modulation for this scenario is showing that the precipitation could decrease up to 30%, which is actually quite a lot for this part of the country. And this is not only an hypothetical scenarios, it's something that we have been already experiencing in the last years, like in this really long event of drought. So we call it like the mega drought event that started in 2010 and ended around 2020. And that affected a large part of the country. In Chile, as you see in these figures, all the red colors are where the precipitation was decreasing extremely in extreme rates, and of course in the central part of Chile. Also, there is not only an event that is occurring, but we see also a tendency in the decrease of snow cover areas in the mountains. This paper was released a few weeks ago, showing that it's not only, like I said, an isolated event, but it's also a tendency that we're observing. And we see that in this basin that they're mostly feeding water resources to this most populated part of the countries are decreasing in snow cover by around 20 to 30% in the last decade. And this has been already showing some consequences on glacier mass balance. For example, this paper, this research work done by Ines Estudiant in 2019 showed that exactly in this period of the drought, we experience a strong change in the behavior of the mass balance, of the surface mass balance for glaciers. So showing in red colors that the glaciers are diminishing, are losing mass, especially related to this dry season. And of course, if there is no snow or rain accumulating in the mountains to be released later in summer, the glaciers will start to release water in form of meltwater, and we see that that can be very important in, this is, for example, one of the basins in central part of Chile, the Maipo River Basin. During dry periods, we see that the glacier contributions to runoff could be reached up to 60%. And even in extreme events, like ones occurred in 1968 and 1969 in the central part of Chile again, this input from glaciers could be reached up to 70% of the water monthly discharge. So it shows that glaciers are actually a quite important component of the runoff for this region. So now I want to focus on one of the most important basins in central part of Chile. So that is Valparaiso, where actually I'm located now. And we are actually supplied by water by this big basin called the Aconcagua Basin, that is covering from the water with Argentina to the Pacific Ocean to the west. And this is it's an important basin because there is a lot of glaciers covering and supplying water for all these cities that are located here, and not only cities, but also some agricultural industry, which is quite important in this part. And we see, of course, that the glaciers are retreating at quite fast rates. In 1955, we have around 150 square kilometers of ice, of glacier ice identified, that has been diminishing up to 118 square kilometers in the last public glacier inventory. And there is a lot of glaciers identified in this region, around 160 glaciers that are actually supplying water for most up to 12% of Chile's national agriculture. So it's why it's so important. In normal years, so we have strong precipitation in winter that is later released as snow melt in summer. But what happens if the snow is not falling, as I showed before? So we know that the glaciers will try to supply this water that is not available anymore as a snow melt. So this is a typical scenario in winter for the Aconcagua Basin in winter. But this at the right side is the typical scenario for summer conditions. So we see that the glaciers are located on the highest part of the mountain, and that is what is releasing water in case that we don't accumulate snow in winter. And this is what the work that we have been focusing in. So two examples of some recent studies that we have been carried out using isotopic techniques and also physicochemical parameters of water. So we have on the right side one results that we carry out in the Chilean side. So we see that during dry periods, the total glacier supply to the runoff could be reached at least 57%, which was much higher than we expected. But on the Argentinian side, so it's looking to the Mendoza region, these supplies can be even more important. So there is a lot of things that we have learned. For example, red glaciers, something that we haven't been able to determine in the past, and we know that it's much more important than we thought in the past. But it's also quite interesting to see that not only the scientific evidence is showing the importance of glaciers, but also the people living there are already quite interested, and they are really know that is the importance of glaciers that are present, and they are supplying water for them. So this is a study that we are carrying out, and it's on the review now, but showing that the population is already quite aware that the glaciers are really important for the water supply for the territories. So, for example, here we see what we estimated using geochemical data of the importance of glaciers to the runoff, but the people already know it's perceiving that the glaciers are important. So they know that rock glaciers are a really important part of the water cycle. This has been carried out in different areas in the mountains here in the Chilean side, and this is something that we want to now to go more in depth with the present project that we are working on. So our plan is to use stable isotopes techniques combined with chemical data to try to understand, like in this example for again for the Aconcagua Basin, to show how important are the sources from water like glacier, periglacial, snow catchment, and groundwater that we don't fully understand yet, and we need to go into more detail to understand what is the real importance of each of these components. So some data that we showed before is that glaciers can be a really important source of water for runoff and also for the people living there. And we know that it's especially important in dry periods, and we know that the scenarios for the future would show that the glaciers will become a more important source of water. So our plan now is to go into more detail and to go even to a micro scale for the studies in the next years. So we started already these field works, and we are now working on this analysis to try to identify with much more detail what is actually happening in these basins in the central part of Chile. So that is what is happening now, and yeah, so I think that is what I wanted to share with you today.
Thank you so much, Francisco. Thank you. I will share again my screen. So as you have seen, isotope hydrology can be used in a very broad area, but also each isotope tells one story. So depending on the research that you are, or the problem that you are trying to tackle, each isotope can give you some answer. So you can always contact us at the IAEA to know more about this technology. And I will just share a last slide. Sorry, this is a bit complicated. As you have seen, each of our speakers presented a problem, a subject they want to treat. But thanks to the IAEA and the research coordinated project, we can gather all these great scientists and make a group of work. Today, for the story, and to give you a nice idea of what is the use of isotope hydrology, we decided to present you the case study from Canada to Chilean Andes. But of course, in this research coordinated project, as I presented earlier, we have scientists from many other regions, including China, including Peru, Slovenia. I will not make the list, but it's a very broad subject, and we are working 12 member states to tackle this problem of melting in glacierized catchment. The idea of working all together is that first we can make a laboratory capacity review, and we can assess the infrastructure available in each laboratory and support each other, for example through exchange of analysis between laboratories or capacity. We can also exchange a reference material specific for glacierized catchment. But this opportunity to work together is also an opportunity for capacity building. The IAEA provides courses and training and workshops on isotope hydrology, but through the coordinated research project, laboratory can also provide training to other laboratories. We will also have joint conference participation, a coordinated sampling effort to create a database and allow data comparison. this opportunity is also a great opportunity to make publication together and to have reference information to compare our data. And the final idea is to include AI, which presented itself this way. How can we use AI to improve our research? How can we use AI to improve the database management and the analysis of the data? So this will go through discussion also between all the collaborators of the project. You can find information on the website of the IAEA. There is a lot of resource available through Isotope directly, information on isotope methodologies, but you can also find information on the coordinated research project activities if you are interested to participate in the future. All the information is also available on the different websites and social media of the IAEA. The main website is iaea.org. And I will now give the space for question and discussion if you have any. And thank you very much for joining this afternoon. It was great to see that we have such a broad audience. Thank you. Please do not hesitate to ask anything you would like to know. Is there anything you would like to ask to our presenters? Anything that is not clear, or how did you hear about the work at the IAEA before?
Hi, Sarah. I thank you for your presentation. And yeah, I'm from China. I'm Taupo, and I have a question about you're doing research on missing, and did you do research as a relationship between missing and reader? Because I ever read a paper showing the good relationship.
You mean a good relationship between subglacial methane and radon isotopes?
Yeah.
Yeah, no, I would have been very interested to go into that area, but personally, no, I haven't been using radon isotopes in these studies.
Oh, okay. Thank you. Because we do some observation on the radon isotopes in subglacial meltwater, and it shows it shows greater variations. And my colleagues also do research on do research just similar your research. So I'm just interested. Thank you.
Yeah, that's very interesting. So do they see a correlation between methane concentrations and radon?
Yeah. Thank you.
Thank you, Del, for your question. If there is no other question, I might have one for you, Sarah. Are you yet within this area of trying to assess the methane emission? What are the next steps, or is it already done? Some mass balance of radon of not radon, sorry, methane emission. Like what are the biggest challenges in doing such mass balance?
Yeah, so a lot of challenges. A very good question. So there have been some estimates for the Greenland ice sheet, because that's where most of the research has been going on, and it's also the longest that the research has been going on there. So with a colleague, we just submitted a paper with an estimate of emissions for the entire Greenland ice sheet. However, it's very tricky because you don't have consistent export of methane, but it varies on very, very short time scales. So it varies hourly, it varies every day, it varies every day of the melt season and in between melt seasons. So if you want to make a very accurate assessment of the export from one catchment, you would have to monitor the methane concentrations continuously in, well, yeah, very, very thoroughly, plus monitor the discharge volumes. And from that, you could then assess what is the export from that specific catchment, although that would also just be the minimum measurable export, because a lot of the methane already degasses as soon as the meltwater escapes from underneath the ice. So a lot of that is lost. It would be a low estimate of that one catchment. And then you really need to do that for every single glacier and glacial outlet where there is methane. Unless the modelers can find a solution how we can upscale it. But yeah, for a global assessment, a lot of work that still needs to be done and a lot of monitoring. Yeah.
Thank you.
Okay, thank you so much. We will close the session because we have reached our time. Maybe you would like Francisco or Gianni give a last word on what is your experience in working through CRP, through the agency. Did it bring anything to your research? What opportunities did that offer to you? If you want to make a last comment, maybe that will attract future collaboration.
Yeah. So the CRP is near. We've had the first meeting last December, but already we have some great like joint ideas. I think that this CRP will bring me some opportunity to test other isotopes or other way of sampling that I haven't thought about before, and that's really powerful of a collaboration to try to go for other techniques.
Last comment, maybe Francisco, before we close this session.
Yeah, totally agree with Jenny, and we are looking forward to also to learn from the other from the rest group, especially we were discussing with Jenny some radon measurements maybe in South America where we have been able to test it again until now. So maybe will be a really great chance to improve how we understand the cryosphere and the water supply in South America.
Great. Thank you so much. Thank you really for presenting and for all the persons who have joined this afternoon on this launching of the year of glacier preservation. I wish you all a very nice evening, and yeah, please do not hesitate to write or contact the presenter or myself at the agency. Sarah is also working at the agency, so please do not hesitate to contact us for anything. Thank you for being here.
Thank you.